Hello everyone. In this lecture I shall discuss the most important series, what is called the Laurent series, right? The Laurent series expansion. So the Laurent series expansion, if you recall your Taylor series expansion of a function fz about a point z0, right? While we find the Taylor series expansion, the function fz is analytic throughout in the domain D, and moreover the point z0 is also a point of analytic, right? It is analytic at z0, also analytic everywhere. It is also analytic everywhere, right? Then taking the center at z0, we can find the Taylor series expansion, right? So this Taylor series expansion include only the positive power, non-negative power of the z minus z0, right? Also this expansion of fz is unique. You will find one and only one Taylor series in a given region, right? And it involves only non-negative power of z. Now the question is, if the function is not analytic at z0, right? If the function is not analytic at z0, right? But it is analytic everywhere. fz is analytic everywhere except at z0, right? Then the Taylor series fails, or not at z0 including its neighborhood also, right? Now once z0 is isolated, it will lead you towards the uniqueness, right? Then the Taylor series fails here. At these situations, it can be addressed by using the Laurent series expansion. So for the Laurent series to work, we have fz is analytic inside and on the boundary of the annular region. Means here we are fz is not analytic at z0. So with z0, so I take a circle here, right? Then it is not analytic within this. So now it is analytic beyond z0, right? Suppose it is analytic beyond z0. It is analytic beyond z0. So this is my, suppose my small r. This is my small r, and this is my capital R, right? This is my capital R. So now fz is analytic here. Fz is analytic here. It is analytic within this annulus. This is called the annular region or the annulus, right? This is called the annular region or the annulus. But it is not analytic inside the small circle. So we take a neighborhood of z0, right? We take a neighborhood of z0, and it is beyond z0, it is analytic. So now for all z here, it is analytic at z. Z is any point here. Z is any point here, right? Z is any point here. Any point you take. Z is a point of analyticity, but it is not analytic at z0, which we are taking the center. So this is the difference. In Taylor series, it is analytic at z0. In Laurent series, it is not analytic at z0, right? So let fz is analytic inside and on the boundary of the annular region D, bounded by two concentric circles. This is my C1 and this is my C2 circle, and this is my C1 circle, right? This is my C2 circle and C1 circle. So now with radii, the radii of this big circle is capital R and small circle is my small r, and both are centered at z0. The common center is at here z0, right? Both are centered at z0. The common center is here z0, right? Now as you know, the Taylor series is unique, right? But to make this Laurent series is not unique. If you take different annuli, right, then we will get the different Laurent series. But to make it unique, right, to make it unique, what is necessary? To make it unique, it is necessary that this z0, the singular point, is an isolated point, right? We don't find any other singularity except z0. Then this Laurent series can also be unique. But in general, without the isolated singularity, we can also have the Laurent series expansion, right? So then enclosed within the disk this, right? This z0, where it is not analytic, it is enclosed within the small disk, right? So now for all z in D, for all z, as I told, for all z in D, right, in the analytic region, the Laurent series expansion, about z0, Laurent series expansion about z0 is given by it is an with positive power of z and bn with negative power of z, right, bn by z minus z0 to the power n, I may write also. So now this is the positive power of z, it is same as the Taylor series. So this part is called the analytic part or the regular part, and it is same as here, this part is same as your Taylor series, this part is same as your Taylor series, right, and with negative power of z, what is called the principal part or singular part, right. So now before the details of the discussion, let me to introduce myself, Professor S.K. Paikray, Kumar Paikray, currently working as a Professor of Mathematics at Veer Surendra University of Technology, Burla, Sambalpur, Odisha, India. So without much delay, let me to tell the details of the discussion. Actually, it is most important, and this Laurent series expansion is important. You find its application in classification of singularity and to find the residue integral, right, residue integral. So it is most important. Again, to learn this Laurent series, we should have a details knowledge on the Taylor series, right, and some standard series as we have written. Basically, the series based on the binomial expansion is most important. Okay. So now without much delay, let me to discuss the details. Now this positive power of z, okay, this positive power of z, this is same as Taylor series. It is same as your Taylor series. It is same as your Taylor series, and it will converge, right? It will converge here when z minus z0 mode is less than r. It will converge this because it is same as your Taylor series. Now this negative power of z, okay, this negative power of z, it will converge if it is beyond this small circle, right, z minus z0 mode less than this small r, right. So now the common of this, it is beyond this small circle and it is below this large circle. So the common region of convergence is nothing but this annulus, right. So they combinedly converge. So what is the common region of convergence here? The common thing, right. What is common here? The common is nothing but the annulus. That means z minus z0 mode is beyond this small r and it is below your capital R, right, below your capital R. So we may avoid the boundary. So we may write it is strictly less than because R may sometimes be infinity. Okay, no conclusion can be drawn on the boundary. So the Laurent series to converge, it should be in the annular region, right. So here in line with the Taylor series, here an is given by this, the integral formula. Here the power is w minus z0 to the power n plus 1, and here the power is w minus z0 to the power here minus n plus 1, right. It is taken in counterclockwise sense. Now the question is, can I merge these two? One more thing, if there is no singularity, if fz is analytic throughout inside this, right, one comment, if fz is analytic, this is my D region, say fz is analytic in D everywhere, then your Taylor series is same thing as your Laurent series. It will involve only non-negative power of z, non-negative power of z. Okay, so that's why this part is the analytic part is same as your Taylor series. So now actually we are not working with this integral formula. Working with this integral formula is a complicated task. So now alternatively, if I set this Bn is equal to my minus of An, right, then I can merge these two summation together. Thus this C, if C is if my C here, C is my any path here. If I take C is my any path here, right? C is my any path here, right? Then I can merge these two integral together. I can merge these two integral together here. So now this combinedly this will be given by n is equal to minus infinity to infinity an z minus z0 to the power n. So here because of minus infinity the negative power involved, because of plus infinity positive power involved, and these two an and bn are combined by this. It is fw by w minus z0 to the power n plus 1 dw. Okay. So for deep understanding this theoretical aspect is necessary. However, to solve problem just use the formula and solve the problem. So now you see fz may have different Laurent series. Fz may have different Laurent series, right? Different Laurent series in two annuli with same center, right? However, for uniqueness in line with the Taylor series, z0 must be an isolated singularity. Okay, we can just have it is a small circle of convergence, just that point convergence, right? That point convergence here, isolated singularity, right? So now as such the small circle should be shrunk into a point z0 only, right? A point z0 only. That means this shrunk into a point only, this point only. Then it is my capital R here. It is my capital R here, right? Now if shrunk into this small annular region, this is my annular region, it is a point only where it is not analytic, then this point is called a isolated singularity and it will lead to the uniqueness of the Laurent series. So mostly we will work in this line, this uniqueness of this Laurent series here. So now the evaluation of an and bn, right, using this integral formula as mentioned is very difficult, tedious job. So usually we use the binomial expansion to overcome this issue. It is possible that the Laurent series expansion may contain only positive power, as I have told, right? Only positive power. Then it is same as your Taylor series. It is same as your Taylor series. When fz is analytic throughout in this domain, including the point z0, right? Then it is same as your Taylor series, and it may also involve only the negative power, right? When this analytic part is identically 0, right? When this part is identically 0, analytic part is identically 0, it is only in the negative power, right? Now when it is analytic throughout in fz at all z as well as at z0, then it is here only positive power of z, which is same as your Taylor series. Okay, so therefore we can say Laurent series is a generalization of this Taylor series, and this Laurent series is most important, right, to learn your residue integral as well as to classify the singularity, which is again one of the important aspect of complex analysis. Okay, so let us now solve some example to make your understanding clear. Now coming to this basic example, find the Laurent series expansion of fz is equal to Taylor series expansion first of fz is equal to 1 by z minus 3. Coming to your solution 1. So fz is equal to 1 by z minus 3. We should write it of the form of 1 by 1 minus z. It is 1 by, if I take minus 3 common, it is 1 minus z by 3. So I can write it minus 1 by 3 into 1 by 1 minus z by 3. So now I know the expansion of this. Okay, so I use this expansion. It is minus of 1 by 3. It is summation of z by 3 to the power n with, I treat this as here x. So this mode z by 3 mode is here less than 1. So you can write it. It is minus of summation of z to the power n by 3 to the power n plus 1 with z mode less than 3. That means the region of convergence here is the center is at 0. The center is at 0. And the radius is 3 here. Okay, this Laurent series will converge over here, right? This is the geometry of this. Now coming to your solution number 2i. Solution 2i, right? Solution 2, it involves I and 2i. Here 1 by z minus 3, 1 by z minus 3. So it has two aspects here. You mark it carefully. Now in the line of the Taylor series, taking 3 3 common, constant 3 common here. So what I am getting, it is minus of 1 by 3 into 1 by 1 minus z by 3. Now taking variable common, taking variable z common. Okay, what we are getting, 1 by z into, it is 1 minus 3 by z. It is in the negative power of z. It is in negative power of z. Negative power of z. It is the positive power of z. Positive power of z. So it is same thing as your Taylor series. So as you know, this is same thing as your summation of, it is your minus 1 by 3. It is minus 1 by 3 is out. Minus of 1 by 3, it is summation of z by 3 to the power n with z by 3 mod less than here 1. So this is equal to summation of z to the power n negative of 3 to the power n plus 1 with z mod less than 3. It is same as the same as your Taylor series. It is same as your Taylor series with the center is here and the radius is this. It is convergence throughout. Now what about this? Now you see here, it will not work at z is equal to 0, right? It will not work. So z cannot be 0 here because z in the denominator. So what will be the series here? So you can write it. It is 1 by z in 1 by z into 1 by 1 minus 3 by z. So it is of the form of 1 by 1 minus z. You will able to write it. It is 1 by z. It is summation of 1 by 1 minus z formula 3 by z to the power n with 3 by z mod is less than 1, right? Binomial expansion. So this is equal to, you can write summation of 3 to the power n by z to the power n plus 1, right, with 3 less than z mod or z mod greater than 3, or you can write it 3 less than z mod less than infinity. So what does it mean? So to understand this, so it is not analytic at 0. Here 0 point is excluded here, right? This point 0 is here. So this 0 point is included. It is the point only. We exclude this point. Now this part is my annulus, right? This part is my annulus here. This part is my annulus here. So right. So it is my infinite radius here. More than, so it is greater than 3 here. Now actually this is the annulus here, right? This is the annulus here. But we are talking about this when 3 less than z mod less than infinity. Now this series is beyond this, right? Means it is here. It is the region here. We are taking this. It is beyond 3. If this is my 3 here, it is beyond 3. We are talking about within this region. This is the Laurent series, right? So we can have Laurent series in different regions. Let me to solve few more examples, then your idea will clear. Now coming to this question. So here you see fz is equal to 1 by z square minus 5z plus 6. So middle term factorization 1 by z square minus 3z minus 2z plus 6, right? So this is equal to 1 by z into z minus 2 into z minus 3, right? So by partial fraction it is a by z minus 2 plus b by z minus 3. Putting z is equal to 2, your value of a will be, so value of a will be your minus 1 and value of b is your 1. So you can write it 1 by z minus 3 minus 1 by z minus 2. As we discussed here, there are two aspects to learn. Taking 3 common, we are getting z mod less than 3. Taking z common, we are getting z mod greater than 3, right? We are getting z mod greater than 3. And here likewise taking 2 common, here z mod less than 2. And taking z common, we are getting z mod greater than 2. So here we have, let it be my a, let it be my b, let it be my c, and let it be my d. Now for question number I to work, it is within 0 less than z mod less than 2, right? If I take this 2 here, then it will work for 0 less than z mod less than 2, right? If I work with less than 2. The second annular region is 2 to 3. It is more than 2, less than 3. If I take more than 2, right, less than 3, more than 2, less than 3, here it will work 2 less than z mod less than 3. Now if I take greater than 2 as well as greater than 3, right, greater than 2 as well as here greater than 3 here, greater than 2 as well as greater than 3 here. So what is the common? More than 2 and more than 3. It is more than 3, right? This is your common here, this is your common here, right? So more than 3. So in that way we have to work. So this is your I, this is your I, this is your 2I, and this is your 3I. Okay, 3I. Now for your I to work in the region 0 less than z mod less than 2 here. So we have to work with this and we have to work with this. So here fz is equal to 1 by z minus 3 minus 1 by z minus 2. So I need to take the common the constant here as I told. So this is equal to minus of 1 by 3 into 1 by 1 minus z by 3, and it is minus plus 1 by 2. It is 1 by 1 minus z by 2. You know the series expansion here. So this is equal to here. It is minus 1 by 3 summation of z by 3 to the power n, right, with z by 3 mod less than your 1 plus your 1 by 2 summation of z by 2 to the power n with z by 2 mod is less than 1, right. So what you can write, if you combine these two, this is summation of here 1 by 2 to the power n plus 1, and here it is minus 1 by 3 to the power n plus 1, and z to the power n is throughout. So this is merged together, n is equal to here 0 to infinity, and here z mod less than 3, here z mod less than 2, right, here z mod less than 3, here z mod less than 2. So the common thing is here z mod less than 2, right. So this series here is 0 less than z mod less than 2 under this region 1, it is there. So now coming to here 2i, here region 2i, here fz is equal to 1 by z minus 3, here 1 by z minus 3 minus 1 by z minus 2. We need 2 less than z mod less than 3. So more than 2 less than 3. So more than 2 means here we have to take z common here, right. More less than 3 means here we have to take 3 common here. So I can write it, I have to take common 3 here. So this is minus 1 by 3 into 1 by 1 minus z by 3, and here it is more than 2 means I have to take z common here. So this is 1 by z into 1 by 1 minus 2 by z. Okay, so this will valid in this region here, this will valid here. So this is equal to, I can write minus 1 by 3 summation of z by 3 to the power n with z by 3 mod less than 1, and minus 1 by z into summation of 2 by z to the power n with 2 by z mod, right, less than 1. So if I combine them, so this will give you minus of summation of z to the power n by 3 to the power n plus 1 with z mod less than 3, and minus here summation of 2 to the power n by z to the power n plus 1, right, it is z mod greater than 2. So z mod greater than 2 and less than 3. So what does it mean? So it is center is at 0, it is greater than 2, it is 2, and it is here 3, right. So it is lies in this is my 0, this is lies in the annular region here. So this is the Laurent series here, right. So what we are getting? We are getting summation of, right, summation of here minus of z to the power n by 3 to the power n plus 1 plus 2 to the power n by z to the power n plus 1, right. It is the positive power of z, it is the negative power of z. So now the region here is the annulus, 2 less than z mod less than 3. Now coming to the third region, here 3i, coming to the third region, here fz is equal to 1 by z minus 3 minus 1 by z minus 2. We have to see 0 here z mod greater than 3, right, greater than 3. So combinedly we have to take z mod greater than 2 as well as greater than 3. So I can take it 1 by z. It is here 1 by z into 1 by 1 minus 3 by z, and here I am taking also, in both cases I need that variable to be common, z into 1 by here 1 minus 2 by z. So here I know the binomial series expansion 1 by z summation of 3 by z to the power n with 3 by z mod less than 1 minus 1 by z summation of 2 by z to the power n with 2 by z mod less than 1. So this is equal to here summation of 3 to the power n by z to the power n plus 1 with here 3 less than means z mod greater than 3, and minus it is summation of 2 to the power n by z to the power n plus 1 with here z mod greater than 2. Now more than 3 and more than 2, right? What is the region here? Right, the region here is suppose I see in the real line here, it is 0 1 2, it is 3. So more than 2 and more than 3, what is the common? It is more than 3, right? So what is the common here? The common is z mod is greater than here 3, and if I add these two together, so this is summation of, right, this is summation of 3 to the power n minus 2 to the power n, okay, into 1 by z to the power n plus 1 with this, or I can write 3 less than z mod less than infinity. So this is the Laurent series here. The Laurent series here is, if you take your center is at 0, right, and you have this annulus, it is radius is 2 and this is the radius is 3, and we are talking about this is the region we are talking about, right, this is the region. So here the Laurent series in this region with strictly negative power of z, right, it is strictly negative power of z means beyond this region. So now here it is both positive as well as negative power of z, means it is within the region of the convergence within the annulus, okay. So in that way we can solve few more problems on Laurent series expansion. So this concept is very, very important, right? This concept is very, very important. Okay, let me to extend to few more problems for your better understanding. So coming to example 3, solution 1. It asks that find the Laurent series of fz about z is equal to 0. So it should be not analytic at 0. You see, since we have 1 by z, so it is not analytic at z is equal to 0, right? So what is here solution I? Here fz is equal to z square into e to the power 1 by z. So z square will be silent here. We have this expansion of this. It is summation of 1 by z to the power n by factorial n with 1 by z mod. Okay, 1 by z mod is less than it is 1 by z less than infinity, less than here infinity. So this is equal to, you can write z square into here 1 plus 1 by z plus 1 by z square factorial 2 plus 1 by z cube factorial 3, so on. The region is not asked here, so that is equal to here z square plus z plus 1 by 2 factorial plus 1 by z 3 factorial, right? So in that way you see it is in the positive power of z as well as in the negative power of z. Next will be 1 by 4 factorial z square, in that way. So it is both positive as well as negative power of z. So in question number 2 we have to express it about z is equal to 2, means it should be in the power of z minus 2 to the power n, right? So in the power of z minus 2 to the power n. So we can express it first, partial fraction a by z plus 1 plus b by z plus 2. Solving here, a is minus 1, b is 2. So it is 2 by z plus 2 plus it is minus 1, a is here minus 1 by z plus 1. Okay. So now this z plus 1 should be written in terms of z plus 2. So this is equal to 2 by z plus 2 minus 1 by z plus 2. Okay, we have added 1 here. So z plus 2 minus 1. Right, in that way we have to express it. or what we will do, you put z in the power of, we need in the power of z minus 2, sorry, it is minus 2. Okay, so it should be in the power of z plus 2. So you put z plus 2 is equal to u, so implies z is equal to here u minus 2. So what you will write it here, fz is equal to 2 by z is here u minus 2, so it is u minus 2 plus 2, right, minus 1 by, this will be here z is u minus 2, u minus 2 plus 1, so that is equal to, you can write 2 by u minus 1 by here u minus 1. So now it is 2 by u, let it be silent, and it is taking minus 1 common, it is 1 by 1 minus u. So now the expansion here is, it is 2 by u plus it is summation of simply u to the power n, right, u to the power n. So that is equal to, you will write 2 by u. 2 by u means here z plus 2 plus summation of z plus 2 to the power n. Okay, so this is the desired Laurent series. The region is not asked anything, right, the region is not asked anything. It is accepted z is not equal to minus 2, and it is throughout z plus 2 mode. I can write it z plus 2 mode less than 1. Region is not asked. So it is simply asked the Laurent series about z is equal to minus 2. So coming to one more example, find the Laurent series expansion near the singularity at 0 and determine the precise region of convergence, right. So actually we are asked in the power of z only. So coming to your solution I, in I, so here cos z 1 by z for the remain silent, and what is cos z? Cos z is summation of minus 1 to the power n z to the power 2n by factorial 2n, and you know here z mode is less than infinity here, so that is equal to, you can solve it, summation of minus 1 to the power n z to the power 2n minus 4 by 2n factorial with z mode less than infinity, right. And if you split it, it will be here z to the power minus 4 minus 1 by 2 z to the power minus 2, and it is here plus 1 by 24, it is here minus 1 by 720, it is z square plus dot dot dot, and here 0 less than z mode less than infinity. This is the region of convergence here. Now if you come to solution 2i, it is 1 by z into z minus 1, 1 by z into z minus 1. We need in the power of z only. So this is 1 by z into 1 by z minus 1. So this is minus 1 by z into 1 by 1 minus z. So just we split it here. So that is equal to, you can write minus 1 by z into summation of z to the power n with z mode less than 1. Okay. So this is minus 1 by z. It is here z to the power n, 1 plus z square plus z cube, like that, and it is z mode less than 1. So that is equal to, you can write minus 1 by z minus 1 minus 1 by z minus z, it is here minus z, then it is here minus z square minus z cube, so on with z mode less than 1. Okay. Now coming to the example 4, the solution I, here fz is equal to 1 by z square plus 1. You will write it 1 by z plus I into z minus I. We need it in the power of z minus z0 to the power n. I need this power. So I put here z minus I is equal to u, implies z is equal to here u plus I. So I can write it. So this is equal to 1 by, this is z is u plus I. U plus I is here z, and here it is z minus I is u. So it is here u plus 2i. It is here z is here u plus I, u plus 2i, and it is here z minus I is u. So this is equal to 1 by u into 1 by u plus 2i, right. So you can write it 1 by u into 1 by 2i taken common here. It is 1 by 1 plus u by 2i. Okay. So now in the precise region of convergence you are only asked. In the precise region of convergence, so we just take the constant common here, right? We just take this constant, in one direction we will move. So this is equal to here 1 by 2i 1 by u, and here it is only one direction we will move, because it asked only that in the 0 less than z minus I mod less than r. So we take only 2i common, right? We move only in one direction. We just take 2i common. We will not take u common, because we need 0 less than u mod less than r. So here it is summation of minus 1 to the power n u by 2i mod to the power n with u by 2i mod less than 1. So this is equal to, you can write 1 by 2i into, this will be summation of minus 1 to the power n. This is u to the power n plus 1, and it becomes also, bringing this to inside, it is 2i to the power n also, and u mod is less than 2i mod. 2i mod is equal to here 2. So what we are getting, minus 1 to the power n, it is u is here z minus I to the power n by 2i to the power n with u is here z minus I mod less than 2. So this is n is equal to 0 to infinity. So this is answer. Coming to here 2i cos z by z minus pi by 4. Coming to 2i, here solution 2i fz is equal to cos z by z minus pi, right, with z0 is equal to here pi. So you put z minus pi is equal to here u, implies z is equal to here pi plus u. So what is here fz? So fz is equal to cos pi plus u by here u. So u, let it be silent. So this is equal to 1 by u cos pi plus u. It is in the third quadrant, it is negative, so it is minus of cos u. Okay, so it is minus of 1 by u, expansion of cos u, summation of minus 1 to the power n u to the power 2n by factorial 2n with u mod less than infinity. So you can write it summation of minus 1 to the power n plus 1. This minus is taken inside, and it is u is here z minus pi to the power 2n, and it is minus 1, this power, divided by factorial 2n with z minus pi mod less than infinity. Suppose you are asked one more question, expand this, the region is the annulus region here. So you have to put z plus 1 is equal to u, implies z is equal to u minus 1. So what is your fz now? So fz is equal to here 7u minus 9 by u into u minus 1 into u minus 3. So this is a by u partial fraction, b by u minus 1 plus c by u minus 3. If you solve it, the value of a will be here minus 3. It is minus 3 by u. Value of b is here 1 by u minus 1 plus value of c is here 2 by u minus 3. So we need what? More than 1 less than 3. So more than 1 means here we have to take common the variable common, is more than 1 variable common. Here we have to take less than 3, means we have to take common 3 common here, right? So what you can do it, first one is silent, minus 3 by u, and it is plus 1 by u taken common, 1 by 1 minus 1 by u, minus 3 taken common, it is here 1 by 1 minus u by 3. So that here we will get what? We will get here u is less than, u mod is less than 3, and here we will get what? U mod is greater than 1. So if you merge these two combined together, it will give you 1 less than u mod less than 3. So this is the idea. Okay, so I can write it. So this is minus 3 by u plus 1 by here u taken common, 1 by u, it is summation of 1 by u to the power n minus 2 by 3 summation of u by 3 to the power n, and here it is here 1 by u mod less than 1, and here it is u by 3 mod less than 1. So now if you combine them together, it is minus 3 by u plus summation of 1 by u to the power n plus 1, right, with here u mod greater than 1, and here minus 2 by 3, it is summation of u to the power n by 3 to the power n with here u mod less than 3. right? So if you add them, so it is minus, so this is minus 3 by z plus 1. Simply I substitute z plus 1 plus summation of 1 by z plus 1 to the power n plus 1 minus 2 summation of z plus 1 to the power n by 3 to the power n plus 1 with z plus 1 mod. Here 1 less than z plus 1 mod is less than 3. Okay, so this is your answer. Coming to one more last example. Now to conclude, we have one important assignment problem. So here fz is equal to, right, 2z minus 3i by z square minus 3iz minus 2. We have to develop in the valid, which is valid in the following region. You see here, first we simplify. Here what is your fz? Fz is equal to 2z minus 3i by z square minus 3iz minus 2. If we simplify it, it is 2z minus 3i by z square, and it is minus 2iz minus iz minus 2, middle term factorization. Okay, so this is equal to your 2z minus 3i by here z into z minus 2i minus I into z minus 2i. So what we are getting? We are getting it a by z minus I plus b by z minus 2i, right, partial fraction. So what we are getting? We are getting, we will get a is 1 and b is 1. It is 1 by z minus I plus 1 by z minus 2i. So now we have, there are two aspects of this. One aspect is z mod less than 1. If I take I common, if I take z common, it is z mod greater than 1. And similarly two more aspect. If I take I common, here 2i, this is 2i taken common, it is z mod less than 2. If z taken common, it is z mod greater than 2. So now you have, let it be your a, let it be a, let it be b, let it be c, let it be d. Now for your 1, we need z mod less than 1 and z mod less than 2, right? It is your a plus c. So this is your 1. Now for your 2, it is more than 1 less than 2. So you need it more than 1 less than 2. It is your b plus c. Then question number 3 is more than 2. So it is more than 1 and more than 2. Okay. It is here more than 1. It is here more than 1 and more than 2. The common is more than 2. It is b plus d. It is here b plus d. Now coming to this 4, we have to shift it. So coming to your 4th, okay, you put z plus I is equal to u. Implies here z is equal to here u minus I. Z is equal to u minus I. Accordingly, what is your fz? Accordingly, your fz will be 1 by here z is u minus I. It is u minus 2i plus 1 by z is u minus 3i. So what we need? We need 0 less than z plus I mod less than 2. Right, less than 2. So we have to find it. We have to take 2i common here. We have to take 3i common here. So it is here 1 by 2i minus 1 by 2 into 1 by 1 minus u by 2i. And here it is minus 1 by 3i into 1 by 1 minus u by 3i. So here I am getting u mod less than 2, and here I am getting u mod less than 3. If I mod these two, the common region is u mod less than 2. Okay. So this will be my answer. So you see, this lecture is quite lengthy, right? But it is lengthy because we have covered so many examples. To make your understanding clear in one shot, right? So many examples are taken. So you should carefully solve it, so that any problem you can approach from any standard book, almost 99% you will be able to solve it. Now if you feel this lecture is useful and interesting, please like and subscribe to this channel, which will boost my motivation to upload subsequent lectures for your benefits. So let us close this lecture here. Thank you all. Have a nice day.